It's the question that always comes up when thinking about the origin of the universe. What came before the Big Bang? And if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including a young Albert Einstein, assumed the universe itself to be eternal and everlasting. Of course, stars could be born and die in it, planets could collide, and civilizations could arise and fall. But on large spatial scales and over long periods of time, it always looked roughly the same as it does now. Only in the 1930s did convincing evidence of the expansion of the universe appear, and in the 1960s, evidence of its origin in the Big Bang emerged. Such a radical revolution in the scientific worldview had not occurred, perhaps, since the recognition of the heliocentric system. But then two equally difficult questions arose. First, what actually was before the Big Bang? What was space like before it began to expand, and how long did it stay in this primordial state? Secondly, everything that has a beginning has an end, so what will it be like at the end of our universe? The English physicist Brian Cox set out to find an answer to this question in a world-shattering revelation. Physicist and professor of particle physics Brian Cox has just declared that he strongly suspects that the universe existed before the Big Bang, throwing the theory of our origins on its head. We used to think that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call that the Big Bang. But now we strongly suspect that the universe existed before that, and in that sense, it's possible to speak of a time before the Big Bang, Cox said. Join us as we dig deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, regularly contributing to public debate and discussion. Never one to shy away from the big questions, the physicist previously took on the story of the Big Bang. The idea of the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding. Today, if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, that means the universe cools as we age, and hence things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backward in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart, a time where matter and antimatter pairs could spontaneously form as the universe was so energetic that pairs of particles and antiparticles could spontaneously be created, a time where individual protons and neutrons break down into a quark-gluon plasma as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, is also understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab. We've created matter-antimatter pairs. We've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements, and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner, except, that is, in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First off, the horizon problem. If we look in different directions, we see the universe as having the same temperature and density everywhere, but even since the start of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with one another. So how did they evolve to reach the same temperature and conditions everywhere? Next, the flatness problem. In an expanding universe, in general, there's a fight between the initial expansion rate that drives things apart and the gravitational effects that work to bring everything back together. In our universe, we observe that these two opposing forces are pretty much perfectly exactly balanced, leading to an exactly spatially flat universe. So, why was our universe born with those properties? And last, the monopole problem. If the universe reached these arbitrarily high temperature and energy conditions, then why are there no exotic leftover heavy relics, right-handed neutrinos, magnetic monopoles, and other particles that should be observable and left over today? We can always shrug our shoulders and mutter something like, "Those must have just been the initial conditions or the way the universe was born." But that runs counter to the enterprise of science. Instead, we look for a mechanism that would mandate and set up these conditions. That mechanism sprung forth in 1980 in a remarkable paper by Alan Guth, who noted explicitly that an early rapid and relentless phase of exponential expansion, where the universe's energy was not distributed among matter and radiation but rather was inherent to the fabric of space itself, would solve all 3 of these problems. But because inflation represents an exponential expansion of space rather than one that terminates in a singularity like the original model for the Big Bang, it sets up a very different picture of the beginning, a whoosh that led to a Big Bang, rather than the emergence of time and space from a singular state. Now we get to address the really big questions. What does all of this mean for the true beginning of the universe, if such a thing even existed? Well, the bottom line might be that the hot Big Bang definitely happened but doesn't extend to go all the way back to an arbitrarily hot and dense state. Instead, the very early universe underwent a period of time where all of the energy that would go into the matter and radiation present today was instead bound up in the fabric of space itself. That period, known as cosmic inflation, came to an end and gave rise to the hot Big Bang, but it never created an arbitrarily hot, dense state, nor did it create a singularity. What happened prior to inflation, or whether inflation was eternal to the past, is still an open question, but one thing is for certain: the Big Bang is not the beginning of the universe. But if the Big Bang wasn't the beginning, what was it? What happened before the Big Bang? Short answer: we don't know. Long answer: it could have been a lot of things, each mind-bending in its own way. It's possible that before the Big Bang, the universe was an infinite stretch of ultra-hot, dense material persisting in a steady state until, for some reason, the Big Bang occurred. This extra-dense universe may have been governed by quantum mechanics, the physics of the extremely small scale. The Big Bang, then, would have represented the moment that classical physics took over as the major driver of the universe's evolution. For Stephen Hawking, this moment was all that mattered. Before the Big Bang, he said, events are unmeasurable and thus undefined. Hawking called this the no-boundary proposal, in which time and space are finite, but they don't have any boundaries or starting or ending points, the same way that the planet Earth is finite but has no edge. Or perhaps there was something else before the Big Bang that's worth pondering. A bold idea of Professor Brian Cox suggests there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Brian Cox proceeded to explain the science creation story. The true story, he says, is an unimaginably violent process that just started with inflation. So if inflation is a feature of the universe, where the universe expands exponentially even before it settles into the hot, dense state that we call the Big Bang, then there could have been many Big Bangs, each with their own universe, and we just happen to live in one of them. Indeed, if inflation did happen, then the Big Bang might have marked neither the beginning nor the end of the inflationary epoch, but simply one of its many stages. The no-boundary proposal and Brian Cox's theory open up fascinating possibilities for what could have existed before the Big Bang. Could it be that the universe was born out of some pre-existing state, or perhaps it emerged from a vacuum fluctuation in a quantum field? The idea that the Big Bang was just one event in an eternal or cyclical universe is also tantalizing, suggesting that there could be infinite worlds with their own physical laws, histories, and destinies. The idea that time, space, and matter themselves began with the Big Bang is now just one possibility among many. Each new theory brings us closer to understanding the true nature of our universe's origins, but the full picture remains elusive. As physicists like Brian Cox continue to explore these mind-bending concepts, we may one day find the answers to the questions that have puzzled humanity for millennia.